Welcome to the demonstration of the Facility Fit tool, which aims to identify potential bottlenecks in a standard CHO MAB bioprocessing facility, leading to significant product loss and then suggest certain debottlenecking strategies to overcome these. Without getting too technical, I'm going to give a brief demonstration of the functions of the tool and how to set up and operate it. So on launching the application, the default tab would be this one, which is named MAB Bioprocess Setting. This tab is dedicated for the user to set up the model with their defined process parameters. The figure here in the middle depicts the standard MAB process on which the tool is based. Right. So the first step would be to go through each of these unit operations and define the parameters. For example, if we take fermentation, um, the parameters which need to be defined would be, for example, things such as the reactor volume or the cell line productivity, the total fermentation time, which comprises the individual cell growth phases. But most importantly is to decide whether some parameters in the unit operation are subject to batch-to-batch variability and hence should be included in the Monte Carlo simulation. This is done by clicking this or checking this box right over here. In addition to this, it's also essential to define the estimated variability of that parameter. This can be altered by using these buttons here or simply typing in the percentage variability of that parameter. This allows the model to create the probability distribution for the inputs into the model. Then this process needs to be repeated for all of the unit operations in the upstream process and downstream process. Once this has been completed, the user should then define the file name for the output Excel file generated by the model simulation. This is merely just to help for easier location of the file for subsequent data analysis, as you'll see. So, for example, if I name this file Monte Carlo dataset 1, and then again, before we can start the simulation, it's also very important to define the number of Monte Carlo iterations which the simulation will run. The default here is 400, but this can be changed depending on user preference. And then another side note, if there's any confusion or you don't know what the procedure is on any of the tabs, there are help buttons located, which once clicked open up a box like this, which gives a sort of brief outline of the procedure for setting up the in this case simulation or data analysis. So once this is done, we can simply start the simulation by clicking on this button over here, and this runs the simulation. So moving on to the data analysis section, I'll show you how to load the files generated by the model and subsequently apply various data analysis techniques to them. So this is the second tab called the bottleneck identification, and it's dedicated to preparing the data for analysis. So firstly, we need to load the step mass loss and step volume Excel files, which are generated by the model. And this is easily done by just clicking on the drop-down menu and selecting the file from the file list. As you can see, the table below here updated with the preview of the Excel file. These tables are not editable, but it's merely just here to sort of give a preview of the data to make sure you have loaded the correct file. So once this is done for both inputs, you simply click on Run Bottleneck Analysis, and you should be automatically taken to the output, which is here, where you can see that the data has been beautifully plotted. So upon analysis of this, we can see that there are two solutions which have been identified. Solution 1, which is implementing a new resin, and solution 2, which is implementing a larger new vessel. Oh, just a side note, if any mistakes have been made, you can simply go back to the inputs page by clicking on this button. And then it's easy enough to go back to the outputs by just switching tabs at the top here. So two solutions have now been identified, and then if you wanted to compare the various solutions, you can directly jump over to the solution comparison tab by simply clicking on this on one of the corresponding buttons, and it would take you to the bottleneck input tab, where you can see that immediately that solution has now been selected and checked for comparison. Before we get on to any more details of this, I want to first talk about setting up the decision tree. So the first thing to do here is to load the file generated by the model. As we recall, we named that Monte Carlo dataset 1. So in this drop-down list, you'll be able to select your file. But as you can see, that the current data file is that what we created. And again, you can see that there's a preview of the data given in the table over here to the right. Crucially, before we create the decision tree, it's important for the user to define the upper bound value of unexpected mass loss. Currently, this is at 5%. This can be 3%, 7%, 10%. It's all up to the user preference, and will typically come down to the sort of value of the product. I'm going to leave it at 5% for now, and you simply create the decision tree by clicking on this button over here. And again, it should automatically take you to the output tab, where you can see a beautifully plotted decision tree. Upon analysis of this, we can see that a third solution has now arisen, which is implementing a new buffer. So to compare this with a previous identified solution, simply click on this button over here, and it'll take you again to the debottlenecking input page, where you can see that now both the new resin and the new buffer have been selected. So on this tab, deciding which solutions to compare is really simple. Simply checking or unchecking will compare or exclude that solution from comparison. So as you can see, we're now going to compare the new resin against the new buffer solution, and you simply do that by clicking on compare over here. And again, you'd be automatically taken to the output tab where the results are displayed. As you can see, new resin is being compared to new buffer, and both of these are being compared to the base case facility, and these are compared in terms of their mass throughputs, their cost of goods, and the overall downstream processing time. If we go back, we can also include the new vessel volume in this comparison. Again, the same procedure where now it's all three solutions being compared to the base case using all three of those metrics. Finally, the last two tabs are just dedicated to giving some background information on the tool, as well as some additional help for any users struggling with the program. Thank you very much.